The four major methods: uranium decaying to lead, potassium decaying to argon. Now we've already mentioned those two. Then we've got rubidium decays to strontium, and one that you may not have heard of, samarium, decays to neodymium. Samarium and neodymium are what we call rare earth elements. They're very rare. They're not commonly found, but we find them in many rocks in very minute quantities, parts per billion, and that's sufficient for the geologist to do the measurements. Now what happens is a rock is chemically analysed for these atoms or isotopes, and so there's no issue about this. There's no question about the quality of the analyses. I mean, you wouldn't believe the laboratories, the monies that are spent on these laboratories. The equipment is first class. If you want to set up a radioactive dating laboratory, you wouldn't get change for a few $1 million. And the work that is done is top class. So it's not an issue that there's any fault with the actual analyses. They're high quality chemical analyses. The real issue is that the numbers, the analyses have to be interpreted to calculate an age. And that's where the geologists have to make some assumptions. They have to assume that all the data was derived by radioactive decay of the parent since the rock formed. In other words, all the sand at the bottom has come from sand falling from the top. That's as simple as that, just using the same analogy. So they have to assume that all the argon they measure in the rock has been produced by radioactive decay of potassium since the rock formed. That makes sense, doesn't it? Because then they do that back calculation that we referred to before. But we also have to assume, the geologist also has to assume that no other process has affected the parent or daughter atoms since the rock formed. What do I mean by that? Well, think of that hourglass analogy, the egg timer, the 5-minute clock, the sand grains falling from the top to the bottom. What if you weren't looking, you set it up, started the process, and you left the room, you left the kitchen or left the room, while you weren't looking, you were gone, someone sneaked in, lifted up the lid and put some more sand grains in. So when you come back and read the clock, it's grossly in error because some other process has affected the quantities of the sand grains. Well, it's the same. Can you imagine rocks sitting in the ground for millions of years without rainwater and groundwater seeping through them, or hot volcanic waters, and not dissolving some or adding some atoms? No. There's no way, because the geologists haven't been there over millions of years to make sure that there hasn't been any contamination or something like that happen. In fact, were the geologists there when the rock formed anyway to see whether there was only parent atoms in the rock? No, they weren't. So it's only an assumption that they make. Notice it's not an observation, it's an assumption. And then the third assumption is that the rate of radioactive decay has always remained constant at the rates we measure today. So in other words, the sand grains have always fallen at the same rate. Now, all those three assumptions have to be made so that you then can calculate how long it has taken for the measured amount of the daughter atom to accumulate from radioactive decay of the parent. So you take the chemical analysis and you do the calculation, and that calculation gives you the age of the rock. Okay? So the issue is it's not the chemical analyses that are faulty, it's the assumptions. Because each of those three assumptions cannot be proven, they're taken by faith. And interestingly, we can show that there are problems with each of those assumptions, as we'll do so in a minute. So just keep in mind this process. It's quite simple. A parent atom decays to a daughter atom, and you have to make those three assumptions. So there are two types. This is just an aside for those with a bit more technical bent. There are two types of ways of calculating radioactive dates. Okay, radioisotope dates. There are what we call model ages or single sample ages. So, for example, we get a sample of a basalt from a lava flow and we measure the potassium and argon in it, and with that one sample we can calculate a potassium argon model age, a single sample age. So these model ages require a knowledge of the initial isotope concentrations. That is, we have to know whether there was any argon in the rock to begin with. We have to assume that there was none, and the calculation of the age is based on that assumption. If all the daughter was not derived by radioactive decay from the parent, then the model age will be wrong. The model age will be wrong. The other type of radioisotope age is what we call the isochron age, and it's calculated from 4 or more samples collected from the same rock unit. And because it involves more than one sample, 4 or more at the very least, it's regarded as more reliable. Because what if one sample was contaminated? Well, it won't plot where it's supposed to on the graph that I'll show you in a minute. So you can actually tell whether any of your samples are contaminated. And so that's why the geological community regards isochron dating as far more reliable. In fact, they do not require any knowledge of the initial concentrations of the parent, of the daughter isotopes. Okay, you don't have to assume all the daughter was derived by radioactive decay since the rock formed. In other words, you rule out, you don't have to worry about that first assumption. But you're still assuming that there's been no contamination. You're still assuming that no other processes have perturbed the system, and you're still assuming that the decay rates have been constant. So this diagram is a little bit complicated, but let me just run through it for you.